In a previous video, we actually showed by mathematical induction how this sum 1 to the power of 2 plus 2 to the power of 2 plus all the way to the power of 2 is equal to a simpler expression, okay, a closed formula for it. Okay, but now towards the end of the video, I actually started a discussion saying, well, that proof was good, but we just checked somebody else's work because somebody else came up with that formula. So now the question is, how do we actually compute that sum, or this sum, ourselves? All right. Now, one attempt to compute this sum would be probably, and I suggest that students do this, okay, we can write some initial terms of this, okay? So if we choose n to be 1, so we get a sum of 1. For n equals 2, we get a sum of 5. For n equals 3, we get 14. For n equals 4, we get 30, okay? For n equals 5, we get 55. For n equals 6, we get 91. And so on. Okay. Now, so maybe one of you can figure out just by staring at these numbers, or maybe writing a few extra, a nice formula for what's happening for this pattern here, a closed formula. So not a formula with this ellipsis here, right? I was having some difficulties doing it, so I kind of gave up on this idea. All right. So what do we do next? All right. Well, I was thinking, so can I relate this sum somehow with lives? Did I ever see anything similar to this? All right. And the idea came to me actually not from 1, 2, 3 up to n for these 2's here. Okay. So I was thinking, where did I see something like n to the power of 2? Well, n to the power of 2 in geometry shows up as the area of a square of side n. So I was thinking, okay, how about we do something like this, okay? So this little square of side 1 has an area of 1 to the power of 2. Then next to it, if we put another square of side 2, we get our 2 to the power of 2. And then next we put the square of side 3, side 4, and so on and so forth. All right. Let's see. Let's pretend that this is a square of side n minus 2. All right. And then next to it, we are going to have a square of side n minus 1. And next to it, finally, a square of side n. All right. So really, this is the natural way, at least to me, different from this way of writing the sum. Okay. Is this of any help? Well, I don't know yet, but fact is that as you solve a mathematical problem, most of the time you cannot be sure from the very beginning that your ideas are really going towards you solving the problem. All you can do is make sure that your work is correct. All right. So now, but at least I have this sum here. Okay. By the way, let's call this sum Sn. All right. So we have this sum as a sum of these areas here. Okay. And by the way, if this is n minus 2, this will be n minus 2. And this will be, because this is n minus 1, this is n minus 1, this is n, so this is n. Okay, we've got these squares here. All right. Now, so here's what I was thinking. With this sum of areas is nice. At least we have some visual representation of it, but it kind of belongs inside a rectangle. Here. All right. So we've got a rectangle of width n, and the length of it is 1 plus 2 plus all the way up to n. So the length of it is 1 plus 2 plus all the way up to n, which is just n times n plus 1 divided by 2. All right? So at least we have a good understanding of this big rectangle. Now, given this diagram, okay, the problem is, how do we compute this area that's not covered by our squares? All right. Now, for one thing, don't get confused by this gap here, because actually there is the 3 by 3 square that follows the 4 by 4. So there's no gap. It's just we have this stairs type setup here. Okay. So all we need to do is we need to compute the area above this sort of area that we care about. All right, so for one thing, let's write the area of the entire rectangle. So it's going to be the width, so it's going to be n times the length, and the length again is 1 plus 2 plus all the way up to n, so it's n times n plus 1 divided by 2. All right, so this is the entire area. All right, so now if we separate these steps of squares, what we get is this is equal to our Sn. All right, and what we need to do now is figure out this area above. Now this area above is one chunk of area. It's just that it's complicated to compute it in one shot. Okay, so here's what we can do for this. We can actually split it into slices. So this would be one slice, this would be another slice, okay, and so on and so forth. Okay, now let's see what we know about these slices. So let's look at the top slice here. At least we know that the width of it is 1. All right, so the width is 1, and the length, it goes from 1 to 2 all the way up to n minus 1. All right, so okay, this being 1 is nice, because at least as a number, this area is going to be equal to the length of it, again as a number, right? So this area, the area of the slice here, is just going to be 1 plus 2 plus all the way up to n minus 1. So this is just going to be n minus 1 times n divided by 2. All right, now how about the second slice? Okay, the width of the second slice is 1 also. All right, so and the length of it is 1 plus 2 plus all the way up to n minus 2. So the length of it is going to be n minus 2 times n minus 1 divided by 2. All right, and so on. We can continue. All right, and let's see what we get when we get close to the bottom here. Well, the area of this slice here. Okay, now, so this area here is a small area. I can choose to write a number, okay, that represents this area. But that area is part of this pattern here. And every single time I've got a number, even if it's a small number as part of a pattern, I'd rather keep it as part of the pattern. So this would be 1, okay, times 1 plus 2. And 1 plus 2, according to this formula, is just 2 times 3, okay, 2 plus 1, all right, divided by 2. And then finally, this little part here is plus 1 times 2 divided by 2. All right, now, are we getting anywhere? Well, so for one thing, we do get our hands on Sn, but we do need to understand this sum here. All right? Now, what is the natural thing to do with this fraction? To me, the natural thing would be to distribute n over here and over here. All right? So I would say this is equal to Sn plus n times n is n squared over 2 minus n over 2. All right? So now, again, I re-emphasize the idea that we need to follow a pattern once we get one. Okay, that's our hope of actually getting sums that we can compute actually. All right, so here exactly how n minus 1 is this term minus 1, we are going to write n minus 2 as this term, which is n minus 1 minus 1. And we are going to distribute the n minus 1 here over to n minus 1 and the minus 1. So this second fraction will become n minus 1 squared over 2 minus n minus 1 over 2. Right? As you can see, we rewrote sort of our pattern. Okay? And we keep going like so. Okay? And finally, if we write this 2 as 3 minus 1, okay, so we get 3 times 3, which is 3 to the power of 2 over 2 minus 3 over 2. Okay? And if we write the 1 as 2 minus 1, we get 2 times 2, which is so plus 2 to the power of 2 over 2 minus 2 over 2. All right? Now, are we making any progress? Or are we just wasting some time here? Well, okay, if I look at this sum, I notice these parts here, n squared over 2, n minus 1 squared over 2. The next term here would be n minus 2 squared over 2, and so on and so forth. Finally, we get to 3 over 2, and 3 squared over 2, and finally to 2 squared over 2. Well, this is nice because this is almost the sum that we care about. All right? Yes, we do have it divided by 2, and there is one term that's missing, but let's see. So this is Sn, all right? So in between these terms highlighted in these red boxes, we can factor a 1 over 2, right? And then we factor the 1 over 2, so we get an n squared plus n minus 1 squared plus n minus 2 squared all the way down to 3 squared plus 2 squared, all right? So we almost get our Sn, all right? It's just that the first term is missing, so it's minus 1 to the power of 2. All right, very nice. Okay, now let's see what's left over here. It's minus n over 2, minus n minus 1 over 2, all the way down to minus 3 over 2 and minus 2 over 2. Well, this is actually a sum that we know because we can factor actually a minus 1 over 2. And what's left from this is n plus n minus 1 plus n minus 2 all the way down to 3 and 2. So we almost get this sum here, okay? So we get n times n plus 1 over 2. It's just that, as you can see here, we stop at 2, so we are missing a 1, so we have to, we put it in here, so we have to take it away. Now again, let's take a break, see if we got something going. Well, actually, I love what I see, because we have here our Sn, and we have here 1 over 2 times Sn. All right? So this is Sn plus 1 over 2 times Sn is actually 3 over 2 times Sn. All right? And we do have some leftover terms, which is minus 1 over 2, right? From 1 over 2 times minus 1, and then this term here, minus 1 over 2 times n plus 1 over 2 minus 1. Wow. So I believe we are in really good shape now, because look, we started off with this expression, and we ended up showing that this expression is 3 over 2 times Sn plus this expression here. All right? Do we have any ellipses in here? No ellipses. So actually this is a closed formula. So all we have to do in order to compute our Sn is move all these terms over to the left-hand side of this equality and then multiply by 2 over 3. And we do get a formula for our Sn. So we actually figured out a formula for Sn ourselves. All right? So sure, there is a little bit of work to do to finish up this problem, okay, but it's just purely algebraic manipulation. So I let the student, eager to learn, move this all these terms over to the left-hand side here and figure out that actually what we get is Sn is equal to n times n plus 1 times 2n plus 1 divided by 6. So we actually were able to come up with this formula ourselves.